All right, cool. Hi everyone, I'm Shadaj. I'm a PhD student at UC Berkeley, and today I'm really excited to share some of the early work we've been doing on combining contextual equality saturation with the relational model in egglog. Um, Before I start, you'll notice I'm not the first author. I am just the messenger today. So Tyler is an undergrad student at Berkeley. He doesn't actually know I added the slide, but he will be applying to PhD programs in fall 2025. So if you really like this talk, admit him as a PhD student. If you don't like this talk, blame me. All right, so contextual equalities. I'm going to dive into a little bit of background and then talk about how we're combining this with the relational model. So the classic thing is you have something like a division, and depending on what you know about these values that you're dividing, you could rewrite this for better performance. So if we don't know anything about x and y, this is the expression we have. There's nothing we can really do to simplify this. But if we know y is equal to 2, then we can do some simplification. So you'll notice this actually isn't just a shift, because if x is a signed integer, we can't just do a shift. We have to handle rounding behavior. Now, if we know that x is positive, then if we only know that, we can just preserve the division. We can't really optimize it. But if we know both of these facts to be true, then I can do the simplified bit shift, right? And so depending on information we know that we might know based on branching or other parts of our program, we might be able to optimize the program in various different ways. So where do contextual equalities show up? So the classic example is when I have a branchy program. So here's like a simple Rust program where I have some branches, and I'm going to be computing the same x divided by y in a couple different places in the program. So under the y equals 2 branch, I know that this is something I can convert into some type of bit shift. In the positive case, I have the simplified version. In the other case, I have the slightly more complex version. And in the last case, I can't optimize this because I don't know what y is equal to. So how do we actually implement this if we wanted to do this in an EGRAPHS model? So one of the kind of the initial attempts might be, oh, I can just have a rewrite rule that says I can rewrite x divided by y into x shift. But this will be wrong, right? It's true in some cases when I have both of the y equals 2 and x positive branches, but it's not true in general. And so I can't put this in my big global eGraph, because even if I apply the rewrite rule for one of these cases, what's to prevent extraction from effectively applying it in the other cases, right? And so we don't want it to be applied in the other branches of our program. So how do we fix this? So there are a couple of approaches that have already been used in eGraphs to handle this kind of contextual rewriting problem. So the most classic one is this context pushdown approach, where we introduce additional nodes in our expressions to keep track of knowledge that we have based on branches from above. So if we consider our expression from before, I'm going to have a rewrite rule that just generates this kind of context node, which is just going to mark the fact that I know that y equals 2 or y is not equal to 2. And I put everything beneath the conditional behind these pieces of context. So I can kind of rearrange my eGraph a little bit. Now the thing that's really important here is the push rule. So the push rule says that if I know a piece of context and have an expression, I can know that same piece of context for all of its sub-expressions, right? So I can push these down so that they're sitting right above the kind of the expressions that we're interested in optimizing. Again, I can kind of manipulate this graph. And the reason these animations are so slow is I want to kind of point to the fact that we're doing a lot of rewrites. The eGraph is expanding quite a bit in the process of doing this. Lastly, we are going to have another application of this because we have another conditional, and so we push this additional context. And finally, we can apply the rewrite rule, right? So now that I have both pieces of context, I know x is positive and y is equal to 2, then I can have a rewrite rule which is safe and correct, saying that when I have both pieces of context as well as this expression, then I can rewrite it. So we're able to eventually arrive at the rewrite that we wanted all along, and we actually notice that, like, depending on which branch we're on, we extract differently, right? So in the case where y was not equal to 2, then I just extract the original version of the program. But because of this context, when I do know both of these pieces of information, I can extract the optimized term. So this is great. It does the right thing. Only problem is it's very, very slow, right? Because I'm introducing all these additional nodes. I have all these rewrites to push things around. So how do we do better? And in particular, there's another issue, which is we don't share rewrites between these, right? So in this case, if I had an expression saying I'm multiplying x by 0 that was sitting under some piece of context, I might use a pushdown rule. But I have the issue where I might know that x times 0 is equal to 0. I can identify that equivalence. but I have to kind of rediscover this in the contextual version because I don't automatically just get the rewrite sharing behavior that I would like. So the other approach to this, which has shown up recently, is colored EGRAPHS. So the idea here is whenever I have a conditional or some piece of contextual information, I'm going to color all my expressions beneath that, right? And so I might have two colors here, one blue for just knowing y is equal to 2, and then purple for knowing that in addition to x being positive. And so I can have certain rewrites which might be context dependent, and these rewrites will be colored as well, right? So these only apply in this purple graph where I can rewrite the division to a shift by 1. And this is really nice because I can extract on different branches, but I do get sharing, right? So because this color kind of adds a layer on top of my base eGraph, if I have my rewrites in my original eGraph, I can also apply them to the colored variation on this. Right, so if I have a rewrite here, but I'm multiplying by 0, I can still get the sharing behavior because I'm not creating a bunch of copies of the expressions underneath these pieces of context. All right, so what about egglog? What I've talked about so far is kind of in the traditional egg eGraphs model, right, where I'm actually reifying this as a graph data structure. But there's been a lot of focus recently on this relational model, where instead I write everything as kind of a data log program. So the focus of this talk is kind of our early work on figuring out the theoretical foundations for what contextual rewriting would look like when we have this relational model. So there are a couple key observations. So first of all, context, kind of more generally, almost always forms a lattice. Kind of all the cases that we've seen, it forms a natural lattice. So if we have some Boolean expression that we know to be true or not, that's a very simple lattice. I either know it's false or I know it's true. If I want constant propagation, so I know the value of y, then I have the simple lattice. These are classic things from program analysis, but it also shows up in the types of context we want to use in eGraphs. The really cool thing is equivalence relations. When we're keeping track of expressions that are equivalent under different contexts, this also forms a lattice. So let's go in a little bit more into that. So equivalence relations, a quick reminder. So we have a set of expressions, and we're going to have a way of kind of drawing edges between these such that it's reflexive, symmetric, and transitive, right? So I have arrows between them, and this forms, and my connected components here form my equivalence classes. And so what this corresponds in egg to the union find, right? So the union find is just an efficient data structure for keeping track of this equivalence relation. What's really cool is that we have a partial order of equivalence relations, right? So we have fine-grained to coarser, and as I add more edges and apply transitivity rules, I kind of go up in this very natural partial order. But what's more interesting than the fact that it's partial order is that it's a lattice. So it has a well-defined meet and join function. So what is meet? So let's say I have two equivalence relations. I know some expressions to be true in one, and I have a completely separate equivalence relation where I know a different set. The meet says, what are the equivalences that I know to be true in both, right? So I just kind of take the edges that overlap between the two. And so we're looking for the coarsest one in this case for the meet, right? So we want to kind of group together as many expressions as you can while preserving the fact that they were equivalent in the original equivalence relations. There's also the dual, the join, right? So if I have another pair, the join actually says, okay, combine the information from these. So I know some things to be true here, some things to be true here. Now let's assume that I know both of these kind of properties or contexts to be true and combine them. We have to apply transitivity in this case, so it's a little more complicated. But kind of hopefully this gets your intuition going on, like, if I have rewrites that are true in two different contexts, and then I have something that's underneath both of those contexts simultaneously, I could use the lattice join to figure out what expressions are common there. So the key trick that we're excited about is that a lot of the focus in existing approaches like colored eGraphs has been you kind of reify this equivalence relation for all the different colors you have in your program. But if you have many, many colors, this can get very expensive. But if we have this kind of lattice structure, instead of actually reifying and materializing every single one of these equivalence relations, we can store a subset of them and be able to materialize ones that we need on demand rather than doing it ahead of time. The next piece is the relationship between context and our equivalence relation. So when I discussed before that the context that we have that we're rewriting with are a lattice. And the exciting thing is that if we have a lattice in our context and a lattice in our equivalence relations, we can actually map between these. Right? So if I don't know anything about both of these contexts, perhaps all these expressions will be independent. None of them are equivalent to each other. But if all of a sudden I know y equals 2, then I can have some rewrites. And I'm going, again, in the same direction in both partial orders here, right? It's becoming coarser as I go up in my context lattice. And if I know x is equal is positive, then all these are equivalent. So again, I have this map between them, which provides a really natural way to figure out where I need to be applying these deltas as I'm introducing new contexts. Now, the last piece to discuss here is where are the E nodes, right? So far, I've just been writing a bunch of expressions on the slides and drawing arrows between them. But this doesn't actually look like the traditional EGRAPHS model. Right, so where am I going to be doing the type of canonicalization and E-class approach? So to do that, we're using this kind of thing from set theory called quotient sets. So if I have a set of expressions and an equivalence relation on them, I can take a quotient set, which derives the set of E-classes I have in my system. So again, if I have my expressions and some errors between them, the quotient set basically takes the dots that are equivalent to each other and fuses them together. And these form my E-classes. So you can think of this, again, as exactly what's happening in your union find, right? If I'm taking my elements and mapping them to these nodes in my quotient set, that's exactly what a union find does with its find API. But we think this is a nice kind of formal grounding for exactly what's going on when you move from the world of just storing expressions and storing equivalences between them to the optimized, efficient EGRAPHS world. Now, the really cool thing, again, is quotient sets also form a lattice, right? So we have lattices all the way down. So if I take the quotient according to some context and take the quotient according to another context, I actually have the same partial order between these quotient sets as these E-classes get coarser and coarser, right? So if I have some E-classes, there's just a direct mapping when I become more coarse to figure out which of these E-classes are getting merged together based on some additional context that I know. And so kind of there's a small kind of variation here where there's a little bit of trickery in quotient sets because quotient sets are still reasonable expressions, but we need some type of canonicalization. We're working on this. We don't have an answer yet for exactly what canonicalization looks like in this world, but we have some early progress on this. And this particular trickery is if I have the same expression that shows up under several contexts, what does canonicalization look like? In different contexts, I might have to canonicalize to different E nodes. But the big picture here, right, is I have lattices all the way down. On the left-hand side, I have my context, right? Things like, do I know something is positive or do I know something is a certain value? And as I kind of go further and further, going into my equivalence relation, going into quotient set and going into quotient sets with canonicalization, I preserve the partial order and these lattice operators, right? So I have a meaningful join and meet that kind of transforms between all these different representations of my rewrites. And so our hope is that we can do tricks kind of from database literature to only materialize some of these. So if I know that certain rewrites require certain contexts, I might materialize those, but I won't materialize others until those rewrites are possible. And so this can achieve a lot of memory savings while still having kind of a nice grounded formal model that looks very similar to the classic relational approach in egglog. So in summary, there are a lot of existing approaches, but these struggle with kind of mapping to the relational model and also reasoning about things like memory efficiency. And so our main observation is that there are lattices all the way down. We can go from context all the way to our E-classes with meaningful meet and join that allow us to kind of keep track of deltas rather than actually needing to reify each of these individual elements. And so what we're hoping to do in our further implementation work is apply this to have smart algorithms for automatically materializing subsets of these equivalence relations rather than all of them ahead of time. And with that, I'd be happy to answer any questions.
All right, thanks, Shadaj. We have plenty of time for questions, so.
So, thanks. Really cool to see this work. Go ahead. Do you think, where do you put the reasoning about, so one of the things having done kind of, here's a context and I'm now going to rewrite in that context, kind of sometimes if the conditions you're imposing are quite complex, figuring out how that that context maps onto what you can actually do under that context is very difficult. So where do you propose to kind of do the reasoning about the context?
Yeah, so are you talking about kind of like how do you define the rewrite rules that are context sensitive? Or,
For example, yeah.
Yeah, so, okay, this is a complex issue, and I think a lot of it depends on exactly what your context is, right? Like if there are arbitrary kind of logical expressions that you might need to simplify, that gets much messier. I will give that, so this is part of the Hydro project at Berkeley where we're doing distributed kind of query and distributed protocol optimization. So for us, the contexts are things like, oh, I know that I have a network at the end of my query pipeline, and so I don't care about optimizations that introduce additional latency in the processing of elements. So these are a bit lighter weight, the types of contexts that we're dealing with. And so for us, the rewrite rules look like a traditional rewrite rule with a static context that we just require for that. But I agree that there's more interesting work to be done when your contexts are more rich and fine-grained. Yeah.
Hi. Hi, thanks for a great talk. Could you say a little bit more about the quotient sets and canonicalization? Like, why is it hard, and what are you planning to do there?
Yeah. So the main tricky part with canonicalization is how. So there is a natural lattice when you do just the quotient set, right? Like I have these points that are being merged together, and I can figure out a mapping. Canonicalization does not fit into that nice lattice world, right? If I picked a canonical node ID, there's no way to do just a lattice join across two contexts and merge those canonical IDs together. And canonicalization is also very tied to kind of using this union find under the hood, because that's kind of where that's how the canonical node ID gets picked. So the messy part is basically like if I have the same expression under two different contexts and I picked a canonical node, how do I fuse those together when I fuse together those different quotient sets? And we don't have an answer for that yet, but we hope to have one soon.
Thanks. So kind of in the same spirit, I'm curious to understand more what you're doing to represent the quotient sets, because if you had asked me half an hour ago before your talk, how do I represent a quotient set in memory, I would have thought a union find is exactly a quotient set. So how is, there seems to be like another step of like you're representing an EGRAPH inside an EGRAPH in some way here. How are you representing these quotient sets?
Yeah, so the primary way we represent the individual quotient sets is still going to be a union find. What's interesting is now we have a hierarchy of union finds, potentially with some gaps in between. And so what's the primary thing that we're kind of investigating is what is the kind of most efficient way to store the metadata for how to map between the different layers of union finds that we have. But kind of in between, they will still look like union finds and have the same kind of API interface as union finds.
Hello, I'm a bit jet lagged, so I may not have thought hard enough about this. But when you have sort of nested colors, does this approach that you're talking about let you share more nodes like between nested colors? Sort of because when we were talking about just the colored graph, it seemed like blue and purple were like completely different colors, and there was nothing in purple encoding that it was nested within blue. So does this like help you share more by having knowledge of that nested structure, if that makes sense?
Yeah, so I will point out the colored EGRAPHS paper also describes this partial order, but it focuses primarily on just the partial order rather than it being a lattice. And so there is an ordering of like this is a stronger context than another, but for us, we have the lattice join and meet, which gives us things like commutativity, for example. Like if I have two contexts, I don't care the order in which the contexts were introduced. And so that gives us a little more power in reasoning about that. Yeah.
All right, let's thank the speaker again.